At 11:41 p.m. on Sunday, July 19th, 2026, the ocean floor ruptured roughly 208 kilometers southwest of Port McNeill on the northern tip of Vancouver Island, British Columbia. A magnitude 5.6 earthquake, shallow, only about 10 kilometers deep, sent shaking across northern Vancouver Island into Victoria and all the way down into western Washington state, with people reporting the tremor in Bellingham, Port Townsend, Seattle, and Tacoma. No injuries, no damage, no tsunami warning was ever issued. By almost every practical measure, the S was a moderate, unremarkable offshore earthquake, the kind that happens in this part of the world several times a year. And yet, seismologists are watching this one closely. Here's exactly why. To understand what makes this specific earthquake worth paying attention to, you need to understand where it happened, because location matters here far more than magnitude. This quake struck inside one of the most structurally complicated, actively studied sections of plate boundary on the entire west coast of North America. The boundary near where the Explorer Plate meets the Juan de Fuca Plate, right at the northern edge of the Cascadia Subduction Zone. The Cascadia Subduction Zone itself is something most people on the west coast of the US and Canada have at least heard of. It's a roughly 1,100 kilometer, or about 680-mile stretch of plate boundary running from Northern California up through Oregon and Washington and into Vancouver Island in British Columbia. Along most of that boundary, the Juan de Fuca Plate, an oceanic plate, is slowly being forced underneath the much larger North American continental plate in a process called subduction. Picture a massive conveyor belt sliding downward and disappearing beneath the continent. Except this conveyor belt doesn't move smoothly. Large sections of the boundary between the two plates are locked together by friction, even as the oceanic plate keeps pushing forward underneath. That locking means stress keeps building, year after year, decade after decade, stored as strain in the rock. Eventually, when a locked section fails, all of that stored energy releases at once, producing what's called a megathrust earthquake, potentially magnitude 8 or magnitude 9, along with a kind of massive seafloor displacement that can generate a devastating tsunami, reaching the coast within 8 to 15 minutes. This is what people mean when they refer to Cascadia's so-called big one, and it is a real, well-documented seismic hazard. Geological evidence, including buried tsunami deposits and tree ring records from drowned forests, shows that the Cascadia subduction zone has produced full-margin ruptures before, most notably a massive earthquake in the year 1700 that geologists have been able to date with remarkable precision. The interval between these major Cascadia ruptures, based on the geologic record, suggests such earthquakes happen roughly every few hundred years on average, which is part of why scientists describe the fault as being due, statistically, for another major event, though due in geological terms can still mean anywhere within a wide window of time, not a specific date. Now here's where this week's earthquake becomes relevant. Near the northern end of the Cascadia system, close to Vancouver Island, the simple picture of one continuous oceanic plate sliding beneath the continent breaks down. The Juan de Fuca Plate doesn't extend all the way north uniformly. Instead, it transitions into a much smaller separate piece of oceanic crust that times sea, all led the Explorer Plate. And the Explorer Plate behaves differently from its larger neighbor in several important ways. The Juan de Fuca Plate moves toward the continent at roughly 4 centimeters, or about 1.6 inches per year. The Explorer Plate moves at only about half that rate, roughly 2 centimeters, or 0.8 inches per year, with some sections apparently moving even more slowly than that. It's also being squeezed from multiple directions at once, caught between the Juan de Fuca Plate, the Pacific Plate, to Antiquí. Speed and direction means the Explorer Plate can't behave like a single, rigid slab of rock quietly sliding beneath the continent. Instead, it has to bend, twist, and fracture internally to accommodate all those competing forces. Scientists studying this region have used seismic imaging, essentially sending sound waves down into the crust and reading the returning echoes, similar in concept to an ultrasound or an X-ray, to map what's actually happening to the Explorer Plate at depth. What they found was more dramatic than a simple crack. They identified major tears cutting through the subducting plate, including one structure extending approximately 75 kilometers, or about 47 miles. Across part of that structure, researchers found that one section of the plate sits roughly 5 kilometers, about 3.1 miles, lower than the section right beside it. That's not evidence of a single, sudden collapse. It's the result of a slow, ongoing process, the plate bending, and fracturing gradually over a very long period, as different sections have moved at different rates and eventually pulled apart from one another. Some parts of this tear zone still generate earthquakes, because the rock on either side remains in contact and continues grinding against itself. Other sections have gone comparatively quiet, which researchers interpret as a sign that the plate may have already fully separated in those specific spots. In other words, rather than breaking apart in one dramatic, catastrophic snap, the northern end of the Cascadia system appears to be being dismantled gradually, piece by piece, creating smaller tectonic blocks, even as the rest of the system continues its slow subduction beneath North America. This is genuinely important context, because it means the plate geometry at the northern end of Cascadia, right where this week's earthquake happened, is measurably more complex and less uniform than the plate geometry further south, off the coasts of Washington, Oregon, and Northern California. So where exactly did this magnitude 5.6 earthquake fit into that picture? This is the part where careful, specific analysis matters, rather than jumping straight to alarm. When seismologists analyze an earthquake, one of the most informative tools available is something called a MOM, Ent tensor solution, often visualized as what's nicknamed a beach ball diagram because of its checkered quadrant pattern. This diagram shows the possible orientations of the fault that ruptured and the direction the rock moved during the earthquake. For this event, the moment tensor show D2 possible fault planes, one dipping at roughly 77 degrees and the other at about 86 degrees, both nearly vertical. And the actual motion recorded was overwhelmingly what's called strike slip, meaning two blocks of oceanic crust slid mainly sideways past each other, roughly the same style of motion you see on a fault like California's San Andreas. That detail matters enormously because it's fundamentally different from what a Cascadia megathrust rupture would look like. A megathrust earthquake happens on a shallow, gently dipping fault plane, the boundary itself, where the oceanic plate held seafloor displacement, which is a major part of why officials never issued a tsunami warning after this quake. Based on the moment tensor data alone, this earthquake looks like it occurred on a steep fault inside the deforming explorer plate itself, not on the shallow, locked megathrust interface where the feared big one would eventually originate. That distinction is reassuring, but it doesn't make the earthquake's location irrelevant. If anything, it helps illustrate exactly why the northern end of Cascadia is behaving so differently from the rest of the subduction zone. The epicenter sat a bit to the west of the main structure researchers have been focused on, a bounder, a feature known as the Nootka Fault Zone, which separates the Explorer Plate to the north from the Juan de Fuca Plate to the south. The Nootka Fault Zone isn't a single, clean fault line. It's a broad zone containing multiple fault strands and smaller associated fractures, consistent with a boundary between two plates moving at different speeds and in different directions. Based on the location and the mechanism revealed by the moment tensor, the most scientifically defensible conclusion right now is that this magnitude, 5.6 earthquake, likely ruptured a steep local strike slip fault somewhere within that broader network of fractures inside or near the Explorer Plate, rather than the specific, already identified deep tear that researchers previously found DISPL, ACED by roughly 5 kilometers. It's also not yet possible to say with full confidence which precise named fault strand ruptured, since a beach ball diagram alone can narrow down the type and general orientation of motion, but can't pinpoint an exact fault line without further, more detailed analysis of aftershocks and additional seismic data. This isn't the first time this specific area has produced a notable earthquake either. Back in 2014, a magnitude 6.4 earthquake sequence in this same general region revealed a fault approximately 40 kilometers, or 25 miles, long, located inside the subducted Explorer Plate just north of the Nootka Fault Zone. The aftershocks from that sequence showed the plate deforming in a direction parallel to the coastline, rather than simply sliding directly beneath the continent the way a more straightforward subducting plate would. That event, along with other earlier earthquakes in the area showing similar strike-slip movement, forms part of the broader pattern scientists point to when explaining why the specific corner of the Cascadia system keeps producing earthquakes that look mechanically different from a classic subduction event. Put simply, the Explorer Plate has a track record of internal deformation earthquakes, and this week's event fits that established pattern. So, is this earthquake a foreshock for something much larger, potentially the long-anticipated Cascadia megathrust rupture? Here's the honest, scientifically grounded answer. There is currently no evidence that it is, but that's a fundamentally different statement from bias. I'm able to guarantee that it isn't. This is one of the genuinely uncomfortable realities of seismology. A foreshock can only be definitively identified after a larger earthquake follows it. Before that larger event happens, if it happens at all, there's no reliable way to distinguish an earthquake that happens to be a faux reshock from one that is simply its own standalone event. What we do know, statistically, is that only a small percentage of moderate earthquakes are ever followed by a larger one nearby. Most magnitude, 5-point-something earthquakes. KES are exactly what they appear to be. Isolated moderate releases of stress that don't cascade into anything bigger. That statistical baseline is reassuring, but it isn't a guarantee, and responsible seismologists are careful never to claim otherwise. What scientists do watch closely after an earthquake like this is the aftershock pattern that follows. If subsequent smaller earthquakes start to migrate spatially, particularly if they trend eastward toward the actual locked megathrust interface rather than staying contained, within the explorer plate's internal fracture network, that would be a meaningful signal worth heightened attention. So far, based on available data, that kind of migration hasn't been reported following this event. It's also worth understanding the basic physics of how one earthquake can, in principle, influence another nearby fault, because this is genuinely established science, not speculation. Every earthquake changes the distribution of stroh, S in the surrounding rock. Sections of neighboring faults, located close to the rupture, can be pushed slightly closer to failure, a small nudge toward an eventual future rupture, while other nearby sections can actually be pushed into what's called a stress shadow, a zone where the immediate likelihood of rupture I.E. is temporarily reduced rather than increased. Passing seismic waves from a given earthquake can also briefly, subtly disturb faults located much farther away, sometimes registering as small blips in seismic monitoring even in distant regions. This kind of fault-to-fault stress transfer H has been documented scientifically along other major fault systems, including growing evidence that smaller secondary fault strands near the San Andreas Fault in California can, under the right conditions, transfer enough stress to influence larger, more dangerous sections of that fault system. For this specific event, though, the physical reasoning points toward a fairly contained effect. The permanent stress change generated by a magnitude 5.6 rupture would be expected to concentrate closely around the immediate area of that relatively small rupture zone, rather than meaningfully loading the entire sea, errance between a moderate, regionally felt tremor and one of the most powerful earthquakes the planet is capable of producing. A single magnitude 5.6 rupture occurring on a separate, structurally distinct fault system inside the deforming explorer plate does not carry anywhere near the energy needed to directly trigger a rupture of that scale on its own. So why are scientists watching this event closely, if the immediate risk assessment is this measured? Because earthquakes like this one function as valuable, real-world data points for an area of active, ongoing research. The explorer plate's internal deformation, the recently discovered tears within it, and the mechanism of earthquakes like the one this week all help researchers refine their understanding of exactly how stress accumulates and releases at this uniquely complicated junction of tectonic plates. Every earthquake in this specific corner of the world adds another data point to models, trying to determine which parts of the broader Cascadia system are genuinely locked and accumulating dangerous strain, and which parts are instead expressing that strain through this ongoing gradual internal fracturing of the explorer plate. That distinction matters enormously for hazard assessment, because a fault segment relieving stress through frequent moderate strike-slip earthquakes is behaving very differently from a fault segment that remains fully locked and silently building toward a single, massive future rupture. This is also precisely why officials and seismic agencies in the region maintain consistent, standing guidance regardless of any individual earthquake. Residents of coastal British Columbia, Washington, and Oregon are routinely in core, age to review household earthquake preparedness plans, secure heavy furniture and shelving that could fall during shaking, and keep basic emergency supplies, water, food, a flashlight, and a battery-powered radio readily accessible. This isn't guidance issued because of any specific new alarming discovery. It's standing advice appropriate for anyone living along an active subduction zone, useful regardless of whether the next moderate earthquake turns out to be, once again, an internal explorer plate event, or something else entirely. It's worth pausing to explain why the 1700 Cascadia earthquake specifically gives scientists such confidence that this fault is genuinely dangerous, rather than a purely theoretical risk. Geologists identified evidence of sudden coastal subsidence, land dropping abruptly relative to sea level, at multiple sites along the Washington and Oregon coastline, along with buried layers of sand deposited by a tsunami, and entire stands of trees killed almost simultaneously by seawater intrusion, forming what are now called ghost forests, still visible in places like the Washington coast today. Tree ring dating of those dead trees narrowed the timing of the event down to the winter of 1700. Separately, and remarkably, Japanese historical records document a tsunami striking the coast of Japan on January 27, 1700, with no local earthquake felt beforehand, what Japanese researchers came to call an orphan tsunami. By cross-referencing the travel time of a tsunami crossing the Pacific Ocean with the Japanese records, scientists were able to pinpoint the Cascadia rupture to the evening of January 26, 1700. That combination of physica, geologic evidence in North America, and independent historical documentation from Japan is part of why the 1700 Cascadia earthquake is considered one of the best documented prehistoric megathrust earthquakes anywhere in the world, and why scientists take the recurrence risk of another Cascadia rupture seriously rather than treating it as speculative. That single, well-documented event isn't the only evidence either. Beyond the 1700 earthquake, researchers have identified a longer sequence of previous Cascadia ruptures preserved in offshore sediment cores, layers of disturbed sediment called turbidites that get deposited on the seafloor when a major earthquake shakes loose sediment from the continental slope. By counting and dating these turbidite layers going back thousands of years, scientists have built a longer history of roughly 40 or so previous full or partial Cascadia ruptures, with an average recurrence interval that some studies place at around every 400 to 500 years for the largest full margin events, though the actual spacing between individual events has varied considerably, with some gaps much shorter and others much longer than that average. That variability is precisely why overdue, a word often used casually when discussing Cascadia, has to be understood carefully. It reflects the fact that it's been over 300 years since the last confirmed full rupture, longer than some of the shorter historical intervals, but well within the range of natural variability seen in the sediment record, not a fixed countdown to a specific date. Modern instruments add another layer to this picture, beyond geologic history. GPS stations planted across the Pacific Northwest continuously measure the tiny, ongoing movement of the ground, movements measured in millimeters per year. And these measurements have confirmed that large sections of the Cascadia interface are indeed behaving as expected for a locked, strain-accumulating fault. The overriding North American plate is measurably being dragged westward and pulled downward at the coast. Exactly the pattern predicted if the plate boundary beneath it is stuck and storing elastic energy rather than slipping smoothly. Scientists have also identified a separate, subtler phenomenon along parts of the Cascadia margin called slow slip events, sometimes nicknamed silent earthquakes. Episodes where sections of the deeper plate boundary slip gradually over days or weeks, releasing some stress without producing perceptible shaking, sometimes accompanied by a related signal called tectonic tremor. These slow slip events don't relieve stress on the shallower, most dangerous locked portion of the fault, the part capable of producing the largest tsunamis. But studying them gives researchers valuable insight into how stress is distributed and transferred across different depths of the subduction interface over time. Coming back to this week's earthquake specifically, it's worth reiterating how seismic monitoring agencies actually process and communicate events like this one in real time, since that process itself is part of why the public response stayed calm and measured rather than alarmed. Within minutes of the rupture, automated systems at the U.S. Geological Survey's National Earthquake Information Center generated an initial magnitude and location estimate, which get refined over the following hours as more seismic stations report in and analysts review the data more closely. The USGS also runs a system called PAGER, which estimates likely fatalities and economic losses based on the earthquake's magnitude, depth, and the population and building types near the epicenter. This event received PAGER's lowest alert level, green, reflecting both its offshore location, far from major population centers, and its comparatively moderate magnitude. Both the USGS and Canada's National Seismic Monitoring Agency, Earthquakes Canada, independently confirmed there was no tsunami threat associated with this earthquake, a conclusion consistent with the moment tensor data showing steep strike-slip motion rather than the shallow thrust motion that generates large vertical seafloor displacement. It's also useful context to know that offshore earthquakes in this general magnitude range aren't unusual for this stretch of coastline. Earthquakes Canada and the USGS have recorded numerous moderate earthquakes off Vancouver Island over the past several decades, including magnitude 6-point-something events in 2018 and 2023, and various magnitude 4 and 5 events in the years between, virtually all of them offshore, virtually all of them producing no damage, and none of them triggering the long-feared megathrust rupture. That track record doesn't guarantee anything about the future, since a single sample of past non-events can't rule out a different outcome eventually. But it does provide useful, real context for understanding that moderate seismic activity in this specific area is a regular, ongoing feature of the region's geology, not a new or escalating anomaly by itself. It's also worth briefly comparing Cascadia to the one modern megathrust earthquake most people already have some frame of reference for, the magnitude 9.0 earthquake that struck off Tohoku, Japan, in March 2011. That earthquake occurred on a subduction zone with real geological similarities to Cascadia, an oceanic plate diving beneath a continental margin, and it produced a tsunami reaching run-up heights of over 130 feet in some areas, overwhelmed seawalls built on outdated assumptions, and caused the meltdowns at Fukushima Daiichi. Japan is one of the most seismically monitored countries on Earth, yet Tohoku still killed roughly 18,000 people, mostly from the tsunami. Scientists studying Cascadia have used lessons from Tohoku, including the discovery that subduction zones can rupture across multiple locked segments simultaneously, producing a larger event than single. Segment models predicted to revise upward their own estimates of how destructive a full Cascadia rupture could be. That's part of why West Coast planners have spent the past decade updating tsunami evacuation maps, building codes in public education, treating Cascadia's hazard as comparable to what Japan actually experienced. That planning work is exactly what earthquakes like this week's serve as a useful reminder to maintain. It doesn't change any official hazard assessment. It's a low-stakes opportunity to check that a household's emergency kit, evacuation route, and communication plan are current, rather than something to think about only after a much larger event has already begun. It's worth being clear about what this week's earthquake was not. It was not a magnitude on par with a megathrust event. It did not produce the type of fault motion associated with the Cascadia interface itself. It did not trigger a tsunami warning, and for good scientific reason, given its steep strike-slip mechanism. It did not, based on any data curves. Logical research, not speculation. The Cascadia megathrust fault is real. Its potential for producing a major tsunami-generating earthquake is real and supported by geological evidence stretching back centuries. And the fact that the plate geometry at its northern end is unusually complex, actively fracturing, and capable of producing earthquakes like this week's magnitude 5.6 event is itself real, ongoing, published science, not exaggeration. If you live anywhere along this coastline, from Vancouver Island down through Washington, Oregon, or Northern California, the most useful response to an earthquake like this one isn't panic, and it also isn't dismissal. It's simply making sure your own household earthquake plan is current, knowing where to take cover during shaking, having a family communication plan in place in case phone networks become congested, and keeping basic emergency supplies on hand. Regional seismic networks, including the Pacific Northwest Seismic Network in the US and Earthquakes Canada, continue to monitor this region closely and publish real-time earthquake data that anyone can access directly. This week's magnitude 5.6 earthquake off Vancouver Island turned out to be exactly what the seismic data indicated: a moderate internal rupture within the complex, actively deforming explorer plate, not a sign that the long-anticipated Cascadia megathrust event has begun. But its location, right at the heart of one of the most scientifically significant and actively researched fault junctions on the West Coast, is exactly why seismologists paid close attention to it, and exactly why events like this one continue to shape scientific understanding of what's really happening deep beneath the ocean floor along this stretch of coastline.